There are exceptions to the octet rule. Elements in period 1 only have the first shell with electrons in it, which can hold only up to a total of 2 electrons. For this reason, these elements do not obey the octet rule. Instead, they strive to have 2 electrons, which is called the duet rule. So helium has 2 electrons and is already, since it already has a full valence shell, it's stable and is a noble gas. Hydrogen has 1 electron and needs 1 more to fill its energy level. Transition metals also don't follow the octet rule because the D shell is filling, and the filling pattern for the D shell is more complex, and we're really not going to talk about it more in this class. Next, we're going to talk about some periodic trends. The elements that are the most similar to one another are those that are within a column or a group of elements. These elements are similar because they have the same number of valence electrons and tend to lose, share, or gain electrons in the same way to achieve an octet. We'll now go on to some more general trends in the periodic table. First of all, we'll look at trends going down the table. Now, as we look through the group 1 elements, we can see that they have all of the same electron configuration. They have 1 electron in the S1 subshell. So they basically have 1 more electron than the preceding noble gas. For this reason, these elements tend to want to lose 1 electron. When they do so, they have an octet in the previous shell, which then becomes the valence shell. They have a stable electron configuration, and they're much happier this way. Now we'll look at group 7A, which is the one that's the group that's right next to the noble gases. For these elements, they have an electron configuration very similar to the next noble gas, but have 1 less electron. So they have 5 electrons in P5. They want 6 to achieve a noble gas configuration. So for this reason, these elements tend to gain electrons to become more stable and form ions with a charge of -1. Now we'll look at trends going across the table. This is period 2, which is the second row in the periodic table. First of all, lithium is got 1 electron in the S subshell, so that if it lost an electron, it would then have 2 electrons in the first shell. So in other words, it would have a complete valence shell. If beryllium loses 2 electrons, it achieves a noble gas configuration. Now, if we look at boron, it gets a little bit more complicated on how to do it. So for beryllium and lithium, the easiest thing to do is to lose 1 or 2 electrons. With boron, it could lose 3 electrons or gain 5. Beryllium and lithium tend to lose electrons because that's the easiest thing to do. When we get towards the middle of the periodic table, it's a little bit questionable what's the easiest thing for an element to do. And elements tend to want to do what's the most easy thing they can to achieve a stable electron configuration, whether that's gaining or losing or sharing electrons. Now we go to carbon, and carbon's right in the middle. It's got 4 valence electrons. It wants an octet of 8. It could gain or lose 4 electrons. Nitrogen needs 3 more electrons. Oxygen needs 2 more electrons. Fluorine needs 1 more electron. And neon is already there. It doesn't want to react because it's got a stable electron configuration already. Another thing that we need to know about periodic trends is that the closer an element is to having an octet, the more reactive it is. So there's a couple reasons for this. So first of all, the ones that are very close to having a stable electron configuration. So for lithium, for example, it only needs to lose 1 electron, so that's fairly easy to do. It's harder to lose 2 or 3 or 4 electrons So it's less energetically favorable to lose those. For lithium, it's quite energetically favorable to lose that one electron. Same thing with fluorine, just needs one more. It's pretty easy to gain a single electron so that it tends to be very reactive. And the ones in the middle of the table too, the electron configuration, when it's half full, may be slightly more stable, so there's like less of a tendency to react. All right, now that we went through the general trends of the periodic table, we're going to talk about other patterns that we can see across and down the periodic table. The first thing we're going to talk about is atomic size, which changes across and down the table. And by atomic size, we mean the diameter of the atom, including both the nucleus and the electron cloud. Now, the nucleus takes up a tiny bit of space, so most of the atomic size is how big the electron cloud is. The other thing we're going to consider is a property called metallic character. When we talk about metallic character, we're not talking necessarily about whether it looks like a metal, like whether it's shiny or conducts electricity. When we're talking about metallic character here, what we're talking about is how easily does an atom lose electrons. The more easily it loses electrons, the more metallic it is. The next thing we'll consider is something called ionization energy, which is related to metallic character. Ionization energy is the amount of energy it takes to remove the loosest electron. So we're just talking about one electron. Some elements actually lose more than one, but the ionization energy doesn't measure that. It measures losing the loosest one. And it doesn't measure adding electrons, it's only losing them. So the ionization energy is a lot higher for nonmetals, which don't want to lose electrons, than for metals, but we'll get into that in a minute. And then the final trend we're going to look at is something called electronegativity, which is a measure of how much attraction an atom has for electrons. So like looking at these last three trends, the first two, metallic character and ionization energy, are a measure of how metallic an element is, whereas electronegativity is a measure of how non-metallic an element is. So obviously, elements that are more metallic are going to be less non-metallic and vice versa. So these trends tend to, the first two tend to follow an opposite direction of the third one. All right, so now we're going to look first of all at atomic size, which is again determined by how far the electrons are from the nucleus. The nucleus itself takes up hardly any space at all, so it's mainly the space that the electrons take up. So if you look at the principal shells, remember they don't really look like these rings, but they do get larger as we go out. So n equals 1 is the smallest shell, and then this only shows up to n5, but the n7, which is not shown, is the largest shell. So if the larger shells are occupied, the atom is going to be larger. So for this reason, as we go down the table, the atoms tend to get larger, right? So each, for example, this is in group 1, hydrogen is the smallest because it's only got an electron in shell 1. Lithium has one in shell 2, so it's slightly larger, and then so on down the table, going down to francium, that it's got electrons in shell 7, so that's the largest one. So, and this is true of all of the elements across the table as we go for all the different groups. As we go down the table, the elements get larger. Okay, now we're going to look at the size going across the table. So as you move across the table, the same shell is filling. So you might think that it's going to get larger, but since they're going to the same shell, the electrons, remember, they're not going into a larger shell, they're going into the same shell. So that doesn't actually cause an increase in size. In fact, the opposite thing happens. So if we look at this, we're going across the table, and this is in period 2, from lithium to neon. The atoms get smaller in diameter. Now, why is this? This is like a little bit more confusing than the other trend. It makes sense that they'd get larger down the table. But even though neon's got more electrons than lithium, it's actually significantly smaller. The reason for this is that the nucleus of each of these has more protons in it, so it's got a larger positive charge, and it tends to pull the electrons in closer, so it actually makes the electron shells smaller as we go across, so the atomic size decreases across the periodic table from left to right, and this is true for all of the periods of the periodic table.
This image from your book summarizes a trend in atomic size. Atomic size increases going down a column and decreases going across a row.
The next trend we'll look at is metallic character, which is the relative ability of an element to lose electrons. Metallic character decreases across the table for two different reasons. First, it is easier to lose electrons when there are few electrons in the valence shell, because losing electrons is more likely to result in a stable electron configuration. So, for example, lithium only needs to lose one. It's got one electron in its valence shell, and it only needs to lose this one to have a noble gas configuration. Beryllium needs to lose 2 electrons, which is still fairly easy to do. It's harder to lose electrons for boron, which needs to lose 3. And when we go over to the other side, fluorine, it would have to lose 7 electrons to achieve a stable electron configuration. By losing electrons, it would much rather just gain 1 electron, which is a lot easier for fluorine. So metallic character decreases across the table for this reason. But there's another reason that metallic character decreases going across the table, and this is because the atomic size decreases, as I mentioned earlier. And what happens is that as the electron shell gets smaller, the electrons are tugged in closer to the positively charged nucleus, where they feel the positive charge, which holds them in place, so it becomes harder to remove them. So if we go across the table, again, fluorine is smaller than lithium, so the electrons are closer in. So fluorine doesn't want to lose electrons for 2 reasons. It doesn't want to lose electrons because it's got a small electron shell where the electrons are very close and feel a strong attraction to the positively nucleus. And also, fluorine cannot achieve a noble gas configuration by losing 1 electron, and it would be very hard to lose 7 electrons. So fluorine really doesn't want to lose electrons, whereas lithium only needs to lose 1 electron, which is easy, and it's also got a larger shell. So lithium definitely wants to lose electrons and has a high metallic character. So down the table, metallic character increases. And again, the reason for the increase is because of the increase in size. If we look at the size of, let's say, lithium, which is at the top of group 1, it's got only shell 2 as the valence shell. That's quite close in. So the valence electron feels a fairly strong pull on the nucleus and doesn't want to be lost. Whereas if we go down to cesium, the electrons lot further out and is easier to lose. Now, this is not to say that lithium is not reactive. It is still a very reactive element, but cesium is even more reactive. So cesium is, in fact, explosively reactive to the point where it's quite dangerous, where lithium is still pretty reactive, but it's not nearly as much as cesium. So basically, to summarize, metallic character increases with increasing atomic size, whether we're going across or down the table.
And this table summarizes these periodic trends.